everything that's written here, you don't necessarily have to have written in your notes. I'll do my best to underline or highlight the things that are most important. But the general gist of what we're looking at, or what harmonic motion is it represents something that's repeated, and usually something vertically going up and down. So one example is an example of a mass, so some sort of weight suspended on a spring. So if we have a box suspended on a spring, it's just going to go up and down and up and down and up and down. In the absence of other real-world constraints, we would expect that to have repetitive motion where the minimum and maximum remain the same. We have these peaks, and it's just going to keep fluctuating between them. So if we model that up and down, or the height of that spring as a function with time, we can come up with a sine function if we're starting at the center, or we could write it as a cosine function if we're starting at the peak. So a mass suspended from a spring is an example of harmonic motion. So let's see. Again, we can model these by using sine and cosine, but the key idea with working with sine and cosines and using them to measure things, so I don't want to do that, is that they have this repetitive nature, and that they keep hitting those high and low points at the same rate. So it's usually as a function of time, where time represents our x variable. That's why we see t on the x-axis. And let's see. And this motion of going up and down, another term we use for that is vibration. But this is something that is a little more physics focused. So we're going to touch on this a little bit today. We're not going to go super in depth into harmonic motion. Just kind of get a little more of a theoretical baseline. But if this is something that catches your interest, it's very physics focused. So this is definitely the important stuff in terms of your notes here. So what we have is an equation describing displacement of an object at time t. So when we're working with harmonic motion, we are using either sine or cosine. And in most situations, we don't necessarily work with things like horizontal shifts or vertical shifts, because with harmonic motion, with it being repetitive, you can choose to start your time or set time at 0 at the center or at the maximum. So we can basically place that sine or cosine function with the middle on the x-axis if we have knowledge of those high and low points. So that's why you don't see like a vertical shift or a horizontal shift, a phase shift written in these functions. The location of these variables is the same as it has been, where that number out front represents our amplitude. Our variable in the middle, usually we refer to it as b. This is the Greek letter here, omega. But 2 pi over that variable always represents our period. So these are things we've seen before, where amplitude just represents that distance from the center to the peak or the center to the minimum. The new term we have is frequency. So frequency stands for the number of cycles per unit of time. So frequency is valuable because a lot of times with harmonic motion, like if we use that example of a spring, maybe the spring is like pressing down on a dispenser or something, and you want to know how many times does it dispense over the course of 1 minute. Then your frequency would tell you that. It would say over the course of 1 minute, it dispenses 6 times. So it tells you how many full cycles or how many periods it completes in a given unit of time. And you'll see the frequency is just the inverse, or not necessarily the inverse, the reciprocal of our period. So our period is 2 pi over omega. Our frequency is omega over 2 pi. Or usually we think about this in terms of B if we're thinking with the representation of our other sine and cosine functions. Just a different variable is being used to represent the same thing. So since period and frequency are just the reciprocals of each other, another way we can find the period if we have frequency or vice versa is just taking 1 over the other. So if I have the period, I can take, if I have the frequency, I can find the period by taking 1 over that frequency. Or if I have the period, I can do 1 divided by it to get the frequency. So that's how we work with those between each other. So we're going to look at a few different examples here today of harmonic motion and identify some characteristics, as well as come up with some equations using those characteristics. Tomorrow we'll continue to discuss more with real-world trig functions, and it's tomorrow that you'll see a little more specific examples, like those similar to like the video of the trampoline. So you'll see something a little similar, like there's an example tomorrow that has to do with a jump rope. Today will feel a little more abstract with harmonic motion. I suppose the only other thing to note is displacement. Maybe a term that's familiar to you, maybe not. It just represents moving something from its place, or moving something from its current position. So that's what our displacement represents. So if we consider like a current position as like the center or the midline of a sine function, a displacement represents that shifting up and down. Okay. Does anyone need more time with this slide? Alrighty. So question 1 here. So the displacement of a mass suspended by a spring is modeled by the function y equals 10 sine of 4 pi t, where y is measured in inches, t in seconds. Find the amplitude, period, and frequency of the motion of the mass. So there are 3 different characteristics we need to find. We need to know our amplitude, we need to know our period, and we need to know our frequency. So amplitude is just our multiplier on our trig function. So we are multiplying it by 10. So our amplitude should be 10. To find our period, we take 2 pi and we divide it by, we used omega as our symbol in the previous slide, or you can think of it as B. It's that multiplier on T. So to find a period of the length to complete 1 cycle, we take 2 pi over, in this case, 4 pi. So 2 pi over 4 pi, those pi's cancel, and 2 over 4 will simplify to 1/2. So we have a period of 1/2. And to find our frequency, a couple ways we can think about it. So frequency, remember, is the reciprocal of our period. So if I know my period is 1/2, that means my frequency would be 2 over 1, or just 2. Box these so it's a little clearer. Or the other way we can think about frequency is it's also omega over 2 pi, or B over 2 pi. So 4 pi over 2 pi, because that's our b value, which again is 2. So what does this information tell us? So an amplitude of 10 means that the mass, starting at the center, goes up a distance of 10 inches and down a distance of 10 inches. If time t represents seconds, and we have a period of 1/2, that means it takes half a second to complete a full cycle, or for the mass to go up, down, and back to center. Frequency of 2, so our frequency tells us how many times it completes a cycle in the given unit of time. So we have t represents seconds, so this frequency of 2 means it completes 2 cycles per second. So it'll go start at our center, go up, up, down, center, up, down, center, in the distance of 1 second. So depending on what this mass suspended by a spring represents, it would be valuable to know how many times it's going to hit its peak or hit its minimum per second. So we're now just identifying some of these characteristics. Only new one really is frequency. It's just reciprocal of period. Questions so far? So in the past, a lot of times we've worked with period just in terms of, like, there was always a pi. Our period was usually like 2 pi over 3 or something along those lines. You can have periods that are not distances of pi. It gets a little more challenging to graph because it's harder to identify, like, those key points, like our pi over 2, our pi, 3 pi over 2, and so on. But you can have periods of any number. It doesn't have to incorporate a pi. Okay. So here we're going to do the reverse. We're going to write now an equation of harmonic motion that satisfies this information. So in terms of your notes, I would recommend including this table. So I'll give you a moment to copy down that table. And I'll talk through kind of what some of these characteristics mean. Okay, so a few things. So we'll talk about the things that we know first. So amplitude is something we've definitely seen before. We have an amplitude of 4 centimeters. That means when I'm writing my trig function, I know my a value is going to be 4. Amplitude is something we've seen. We have a period of 6. So remember, we find period by, so whether we have a sine or cosine function, so I'll just consider it sine. Our period comes from that b value, where our period is always 2 pi over b. So if I want to write an equation of a trig function, knowing the period isn't as helpful as knowing what b is, because we need that b value to write our function. So we know 2 pi over b is going to equal 6. Since 6 is our period, and the way we find period is by doing 2 pi over b. So we would need to solve for b here, which may be a little hard to differentiate b and 6 here. The b is this one down below. So we could cross multiply b times 6 and 2 pi times 1. So we get 6b equals 2 pi. Divide both sides by 6. And I'm going to get b equals 2 pi over 6, or pi over 3. The last thing to discuss is this first characteristic, displacement. So displacement refers to position or movement from the starting position. So generally speaking, when we're working with these trig functions, our starting position is on the x-axis. So depending on unit of measurement, like 0 inches or 0 centimeters for our y value. So with most of these, we're working with these as a function of time. So instead of working with x, we'll be thinking of it in terms of t, like we did on this previous problem. So a t value of 0, if we think about this visually, so we have our t or our x-axis and our y-axis. A t value of 0 with a displacement of 0 means our mass has not shifted from the center. It's not above the x-axis, it's not below the x-axis, it's at its center position. So displacement of 0 at t equals 0, that means we are starting at the origin. So what this tells me, because we are starting at the origin, at the center, it tells me we should be writing this as a sine function. You'll see with our next problem, and we will finish this one, our next problem has displacement at 3, not at 0. Our next problem, because our displacement is at the peak, it's going to tell me we need to write it as a cosine function. So your displacement essentially tells you what type of function you should be using, whether that's sine or cosine, because sine always starts at 0, 0. Cosine always starts at the maximum. So when we're writing our final function then, we have y equals our a value of 4, it's a sine function, a b value of pi over 3, so sine of pi over 3, t. So that comes from taking in all those different pieces of information and plugging those into our sine function. Any questions so far? Next says, what is the frequency of this harmonic motion? So frequency, remember, is the reciprocal of period. So if we know our period, we can find our frequency. So our period in this case is 6. So our frequency would be 1 over 6. So what that means again, so frequency represents number of times, or number of cycles we complete in the given unit of time. So our given unit of time is seconds. Our frequency is 1/6. So that means we complete 1/6 of a cycle in a second. So there's that inverse relationship between period and frequency. So again, you may be wondering, what's the value? Where is the application with this? Feels very abstract. Well, if you have anything that shows some sort of repetitive motion, like a sine or cosine function, so we represented it as a sine function with an amplitude of 4, a period of 6. So it's saying, depending on what it is, it reaches its height at 4, its minimum at -4, and it takes 6 seconds to complete a cycle. So being able to write a function of that allows you to be able to answer questions about the future. So if this is representing, it's easy to think about it in terms, because it's a spring, a lot of times with springs, when they reach their maximum or minimum, they may push a button or something. Or I talked about how it might dispense something. So it would be valuable because you could plug things into this function, plug in time, and say what happens at 100 seconds. Where is the location of this spring? So if you're able to model that, then you can make predictions or assumptions about the future by using that function. Okay. All right. For number 3, again, we are also creating another harmonic function. So I'll give you a few minutes to try to start this one on your own. Notice for this one, our displacement is at 3. which you'll see because the amplitude's at 3, that means we are starting at the maximum. So you should be using a cosine function when you are writing this. Let's see, I don't have a timer. I will give you about 3 minutes. Come on. To work through this one. So let me get a timer quick. All right. A minute later, we have our 3-minute timer. And then we just have one more problem to talk through. All right, so starting to walk through this one here. Amplitude's 3, our period is 1.5, so when we're writing our function, we have to determine our b value. So 1.5 equals 3 pi over 2. 1.5, or 1.5 equals 2 pi over b. 1.5 as a fraction is 3 over 2, which may be a little more helpful when we are solving for b. You can solve for b still with it as a decimal, but fractions might be more helpful for us. So we can cross multiply 3 times b and 2 times 2 pi is 4 pi. Divide both sides by 3, and I get b equals 4 pi over 3. So now when I'm writing my trig function, it'll be y equals 3, my a value, cosine. It's a cosine function because we are starting at that peak. That's what our displacement tells us. Of 4 pi over 3, because that's our b value, t, because it is a function of time. And that would be our final. That should be a 3 there. There we go. Questions on problem 3? Okay. So a lot of what we've been doing with with writing equations, given some characteristics, just a little bit different format with terminology here. For our last problem here, we're going to look at an example that's a little bit more descriptive. So what we have is we have a tuba player, plays the note E, and sustains the sound for some time. So if we're playing the same note, sustaining the sound, the same level of volume, we're assuming that that sound wave is remaining the same. So the fact that it's being sustained is important. So for a pure E, the variation in pressure from normal air pressure is given by V of T, so volume as a function of time, equals 0.2 sine of 80 pi T. So V of T just means like the same thing as a Y value. So don't get tripped up by that. It's just function notation. Where V is measured in pounds per square inch and T is measured in seconds. Part A says find the amplitude, period, and frequency of V. So we have our equation, so we can find our amplitude, period, and frequency in the ways that we have. Amplitude is just that number out front. So 0.2. And period, we find by taking 2 pi over our b value. So our b value here is 80 pi. So we'll have 2 pi over 80 pi. That's meant to be an arrow. Which simplifies then. Pi's cancel. 2 over 80 simplifies to 1 over 40. So my period is 1 over 40. So it takes 1/40th of a second to complete a full cycle. Next, my frequency. So frequency we know as the reciprocal or opposite of period. So if period's 1 over 40, my frequency would be 40 over 1, or just 40. So we complete 40 cycles, or our sine function goes up, down, and back to center 40 times in 1 second. This frequency represents number of cycles in the given unit of time. And our given unit of time is second. Okay. So if I were to graph this, it's a sine function starting at 0 with amplitude of 0.2. And it doesn't ask us to graph it, so you don't necessarily have to. But it would look something like this, where it takes 1/40th of a second to complete that first cycle. So that should be 1/40th. And by the time we reach 40 seconds, or sorry, by the time we reach 1 second, it will have repeated this cycle 40 times. That's what that frequency represents. So again, what we have here is we have a function of time, so that would be our x-axis, a t value. and V of t is our Y, which represents pounds per square inch. So part B says if the tuba player increases the loudness of the note, how does the equation, so the one given, how would the equation for V change? What do we think would be different if we increase the loudness of the note? Any thoughts? For virtual or in-person students? For virtual, you can click the raise hand button. Morgan? Yes, the amplitude would increase. Why do you say that?
Because like louder waves is like larger waves. Okay.
That's good. Morgan said louder noise would be larger waves. That's correct. So our V of t represents pounds per square inch of air pressure. So if we want to have a louder note, it means we're going to have to play our tuba louder. We're going to have more air pressure. So our amplitude will shift. Our peaks will get higher and higher. Because we're playing the same note, that doesn't mean the period and frequency will adjust. Because if we elongate it or shrink it, it's going to give us a different sound. So the only thing that will change is the amplitude will increase. So part B is more of just a kind of a conjecture about what we're doing in part A. Understanding the ins and outs of the way sine waves connect to music and playing instruments isn't something you'll be assessed on necessarily. So you're not going to have to answer a question like B necessarily on the assessment. More so, you'll see stuff like A. Okay. So that's the conclusion of our notes for today. Tomorrow you do have another lesson. It's a short video along with an IF tomorrow as well that will get into some more specific examples about modeling or coming up with trig functions given not only just given like amplitude and period, but given a set of data. So like how do I interpret the data about the height of a tide and model that by a sine or cosine function. So that's what you'll be spending time with. So make sure you log on tomorrow for that end of the week at a glance for that video. It is a pretty short one. I think it's like 10 minutes. And you'll also have an IF tomorrow. But for now, you've got 10 minutes left to get started on your IF for today. Identifying amplitude, period, and frequency for some functions, as well as writing out those functions too. So head to Google Classroom and please get started on that IF. If you have questions as you're working, please let me know. I'm here to answer those and help you out. Or if there are any issues with the IF, let me know too.